Since we live in a world where many computers have multiple cores that things can be run on, and that our computers often have multiple sort of buffers and pathways for things, then it can often be very useful to split up the work of a program into multiple different threads. It allows different threads of control. So a simple program has only one thread. Each thread will have its own stack and its own program counter to be able to keep track of what methods have been called and restore things and stuff like that. All threads will share all objects, meaning that these are shared memory programs, which will be different than some of the non-shared memory programming techniques we'll learn later. Threads in Java do have a priority mechanism, but it's not necessarily a good one or one that you want to rely on entirely. And they do have methods for synchronization, allowing cooperation and collaboration between programs. We'll see examples where if two threads try to access the same data structure or even the same simple variable at the same time, this can cause problems. And the solution to that will be synchronization, which we'll get into a little more depth on later. But in general, threads can be a really good tool for having our program do multiple things at once or do the same thing in multiple different threads, like our server serving multiple clients, each in their own thread. Here's an example of creating a thread in Java. You can define a class that extends thread, you give it a run method, and then you create an object of that type, and you tell it to start. So that's one way to create a thread in Java. Another way to create a thread is to create something that implements runnable and pass that into a thread's constructor. Then we can create just a basic thread object. We feed it our runnable object, whereas the other one was a class which extended thread. There's not a huge amount of difference for our purposes between the two of these. Both of them will take a run method, and the question is just whether the thread is your object or whether the thread is given your object. In both cases, we're going to have a thread, and we're going to tell that thread to start running when we're ready. We can also use anonymous classes for our threads. These are pretty common. For instance, if you're writing a server and it's going to be spinning off a new thread for every client, and that thread will only ever be used inside of the server class, then you might be able to just write that thread inline. Where you want to create the thread, you say new thread, because thread will be the parent class. And then inside of the brackets, you define the details of your new anonymous thread class, which mostly needs a run method, maybe some other things. And then you call start on that new object that you just created. So this shortens things and it makes it so that it's not exposed like a nested class that's public would or things like that. And similarly, we can pass a new runnable into the constructor of a thread, creating an anonymous class that implements runnable here, where we say new runnable, and then inside the brackets, we define the details of that runnable object that we're going to create. Again, very similar for our purposes. These don't make a huge difference. They're not even that hugely different than the previous examples, except they are anonymous. They have no name attached to them, no class name. The both beautiful and sometimes terrifying thing about threads is that their execution can be non-deterministic, meaning it's not always possible to predict that thread 1 will do its work first and then thread 2. They don't always necessarily take turns, especially if they're executing on multiple different cores. Then they're going to be doing their work at the same time, And even if they have to take turns on something like sharing a buffer and printing to it, who gets the first turn and the second turn and so on is not always well determinable. So here we have a printer class that implements Runnable. It's going to be given some token, and it's going to print that token over and over 1,000 times. And then it will print a blank line at the end. We create two printers, a printer for stars and a printer for dots. And then we create new threads with those runnables, the star runnable and the dot runnable. These are just names for the thread. You can provide names to your threads so that it's easier to tell which thread is doing a thing. So we're doing that here. And then we tell them both to start. It might be easy to assume that because the star one got called its start first, that all the stars might print first, or even that a star might print first. But that's not always necessarily true. It's probably usually going to be true that a star will get printed first, but not necessarily, depending on what else is going on the machine at the time that this is called and started. So here's what you might typically expect. This is what you would expect from a sequentially written program that only runs in one thread, all the stars, then all the dots. You might sometimes see a good number of stars because before the dot thread can start, then we might print a lot of stars, and then the star thread finally gets its chance to start, and it does some of its work, and you can see them intermixed a little bit, but not a huge amount. That might also happen. We could increase the amount of sort of uncertainty here by giving our thread some useless work to do. So we have our thread just loop for a while here, a simple for loop that does nothing, but it goes from 0 to a very large number, I think 1 million. So this is the same as our printer before. We're going to print those tokens, but in between each token printing, we waste some time. That will cause a little more uncertainty on who comes back first and who gets to take their chance to print the second, third, etc. tokens. We create everything else the same way, the stars and the dots, and we start them in the same order. It could look like this, where the stars print only a few and then the dots get mixed in. It could look like this, where only a single star happens and then some dots. It really, again, will depend on how the resources are allocated, how many threads are how many cores are available, what other programs are running, and sort of get mixed in. Lots of different possibilities could cause different behavior on this. So you can imagine that this can cause a lot of complications in your program if you are relying on some job to finish before another starts, or for some pairs of variables to always be aligned. For example, if my two threads were increasing X and Y, or something like that, they were editing a linked list where nexts and previouses both need to get set, then this kind of interleaving could be very bad. If the two jobs are okay to be completely independent, then this kind of interleaving is beautiful and perfect. I want it to be mixed together so that if I'm writing to one file and writing to another file, those two files get created and I don't have to wait around for file 1 to finish and file 2 to finish. This is the sort of thing that something like a BitTorrent client does really well. It's getting different portions of the file from different people who are serving it up, and therefore it's able to get the whole file much more quickly. But if there is interaction between those threads, which often there will be because the purpose of threads is that they share memory, all variables are shared between them, then we're going to have to work on making sure that the things done there are safe. And so threads give us this beautiful benefit of taking on multiple tasks, handling multiple clients, using multiple cores to get a job done, but they also are going to share memory and possibly affect each other in ways that will sometimes cause problems. And that's what we'll look at in the future, is to think about how our threads can work well together.